let's continue our discussion of waves. So, we're going to talk about boundaries. So if we have a wave attached to a boundary, we can send a pulse through it, and depending on what kind of boundary we have, the pulse is going to reflect back differently. So the first kind is a free boundary. A free boundary means it's attached to the boundary, but it's allowed to go up and down. So you can imagine kind of maybe you tie a rope to a pole. The way you would tie a rope to the pole is you would have to loop it around the pole. You wouldn't have a way to firmly attach it necessarily. And so if you just looped it around so that the rope can slide up and down, you get something like this. And so if that's the case, you can see from this image, the rope will go through, and then because it's loose, that thing's going to go up, and so it's going to be reflected back upright. So free boundaries result in a reflection upright. On the other side, if we have a fixed boundary, if we tie it in a way that the boundary can't, or the rope can't move at the points, you actually get this weird reflection where it inverts after it hits it. So free boundaries are upright and fixed boundaries are inverted. Going into that a little bit deeper is instead of just having a different boundary, we can switch materials. Okay, so let's say we have a rope where half the rope is less dense, is like a string, and then the other half is like a thicker rope. It's more dense. Okay. In those cases, when you go from a less dense to more dense, what happens is you send the pulse in, like in the top image, and then part of the wave is going to continue like normal. That's going to happen in either case that we're about to talk about. We're about to talk about more dense to less dense. Either way, some of the wave is going to continue upright. But when we talk about less dense to more dense, it kind of acts as if there's a fixed boundary, in which case part of the wave gets reflected back inverted. On the other side, if we have more dense to less dense, since it's less dense, it acts more like a free boundary to it. And so again, some of the wave is going to continue. It's going to be transmitted and down the line, but some of the wave is also going to be sent back reflected and upright. All right, another term is interference. Today we just have a lot of terms, a lot of different ideas of wave. They're called wave behaviors, so different things waves can do. So interference. So when two or more waves meet, they will interact with each other, and we call this interaction interference. So just when waves meet, they don't necessarily always cancel out or like conflict with each other. They have something called interference. Okay. We have something called constructive interference. So constructive interference when two waves and they meet crest to crest, okay? And so if two waves meet and their crests are meeting at the same time, they will amplify each other. And we call it constructive interference. And you can see this in the ocean. We can play this video real quick. If we have these big waves, there's a wave coming back towards the other wave. You can kind of see it up front. And then that's when you get constructive interference. The waves combine and you get this big wave. Destructive interference are when the waves combine in a way that the crest matches each other's troughs. So you can see here, if we have a wave where the crests are matching with the troughs, they end up canceling each other out and we get no wave. And we call this destructive interference. This is used in your headphones. If you have noise-canceling earbuds, like maybe iPod Pros or whatever, they actually have little mics on the outside of the AirPods. And whenever the sound gets transmitted into the AirPod, it reads the sound and then it'll give off a sound that will give destructive interference to whatever sound's going through the mic. And so it'll use destructive interference to cancel out sounds coming in. And obviously it's not perfect, but it can do a pretty good job if you have them. And they're fairly quiet. They're not the best in the world, but they're pretty good at destructive interference. And so combining those two ideas, we have this principle of superposition. Okay, so when we have two or more waves and they cross a point, essentially the overall displacement at that point is going to be equal to the sum of the displacements of the individual waves. And so essentially we're just going to add up the numbers at a specific point. And so this is going to kind of demo it. Imagine where when this is high, when this is low, you'll see that they cancel out. when they match at highs, let's see, like right there, it was at a high. We can see when this goes a low, they're opposites. It's kind of hard to see while it's moving, but you should be able to do some examples of this. So really what I'm going to do in class is I'm going to explain this through a worksheet, and I uploaded the worksheet online already. It's better explained through some examples. And so the worksheet's up there with the key. The key should be, I actually just found it online, so the key should be linked as well. And so you should be able to go through and kind of check your work. You're basically just going to add the waves. And so if you have a wave, you know, that's like at y equals 2, and then I say add it to a wave where the wave is at y equals -1, well, the resulting wave, of course, is 2 plus -1. So you would a resulting wave of just 1 at that point, and so on. And so you can practice it and see how it works in that example. We have something called the Doppler effect. We're not going to get too deep into it. I figured I just don't really care to get as deep as I could. But the idea is that the change in whenever you have a sound source and something that's observant, so we call it an observer, but whatever's just hearing the sound, if they are separating, if they're moving relative to each other, so they're not just standing still relative to each other, one of them's moving in either towards or away from each other, then we get something called the Doppler effect, where the frequency of the wave changes. And so there's a good video on it. I recommend just watching this video. It explains it really well and makes it more visually appealing to see it. A lot of the stuff you really kind of need to see videos for. And so here's a video. But the main things you need to know is that if the observer and the sound source are moving towards each other, that means the waves are hitting each other more frequently. And so your frequency increases. And on the contrary, when they're separating, frequency decreases. And of course, with sound, we'll study this a little bit more later. When you increase frequency, this means pitch is also increasing within sound. And when you're decreasing, that means pitch is decreasing as well. But this can be any kind of wave. This can also be light when things are, and you'll see this in space, when things are moving far away from each other in space, you get different frequencies. You see different colors because of it. And so there's actually a couple videos here, I guess. I'm not sure. I know one of them is a good, like, just how-to video. I'm not sure what the other one is. I'm forgetting. So I'll have to go back through it. Lastly, this is probably the main difficult part of the day, is standing waves. The only really it's not really that math heavy, but it has a little bit of math in it. We have standing waves. A standing wave is a wave that oscillates in time, but whose peak amplitude profile does not move in space. That's the more verbal definition. The better definition is just looking at this and seeing what a standing wave looks like. It just means that the wave is basically, it looks like the peaks and the crests are moving, but then we have these points that we'll call nodes here in a second that look like they're not moving at all. Okay. And this occurs when you have a wave vibrating in a closed space of some sorts at just the right frequency, so that matches the closed space. And so when we get these standing waves, we get something like this. It doesn't look like it's traveling. It looks kind of like it's standing still, but going up and down. These points that aren't moving, we call these nodes. And then that means all these other points that are going up and down, right, like there, that point that's going up and down, we call it an antinode. And so it turns out there's, like I said, at just the right frequency, but there's actually multiple frequencies. They all have to be precise. There's all a number for them. You can't just have a random frequency, but there are multiple frequencies that can produce standing waves for a given space. Okay? And we call those frequencies, they're harmonics. And so maybe if you're in band or orchestra or a choir or whatever, you may have heard that term before. You may have heard about harmonics. Harmonics, we'll get more deep into harmonics here in the next unit, or the next section, I mean. But today you just need to know that the frequencies that cause standing waves for a given space are called harmonics. And to be called the nth harmonic is just how many bumps there are in a standing wave. And so for this first wave, if we have a wave that's vibrating just one bump up and down, we call it the first harmonic. A wave that has two bumps vibrating up and down, we call the second harmonic. You can also think about it as counting the nodes, or counting the antinodes. Here, there's two nodes. There's one here, and there's one here, but there's only two antinodes. One right there. You might be confused because you see two here, but this really, the red is at one point and blue is the other point. That's kind of how we draw standing waves. We draw the wave at the two amplitudes in time, but it's one wave. If we saw a picture of it, it would be one line going up and down. And so there's one antinode here. And so as we go on, we get 3 harmonics here, and then we get 4 harmonics here. Because there's 1 bump, 2 bump, 3 bump, 4 bump. And so to find the length of the tube for any given wavelength, and you can find the nth harmonic. Sorry, let me explain this again. If you're looking for the nth harmonic of a certain wavelength and you know the length of the structure you're talking about and you know the wavelength, you can solve this for n. So this is just a relationship between the length of whatever you're talking about, the wavelength of the pattern, and then the nth harmonic. So maybe the first or the second or fourth harmonic. So let's really do an example to really try to explain that better. If we have a rope of 1.2 meters long that is vibrated, find the wavelength of the first, second, and third harmonic. Okay. So what I'm saying is I have some sort of rope that's vibrating over here. Okay. It could be going as many times as we want. If we're doing the first harmonic, remember what that means is it means we have one antinode. And so if you wanted to draw like an actual point in time, we would draw it like this. This is what the first harmonic would look like. However, as notation, normally we draw both at the peak and at the trough. And so we will also draw later in time, this vibrates all the way down here as well. And so this is how we would draw a standing wave for the first harmonic. In this case, we know that this total length, L, is equal to 1.2 meters. And we know we're talking about the first harmonic. And so we can find the wavelength for this because L is equal to n over 2 times wavelength. And this means that 1.2 is equal to 1/2 of the wavelength. And hopefully this makes sense. We're saying that this whole wave is 1.2 meters long. And really, we know what a wavelength is. A wavelength is one whole cycle. But if you look here, this is only half a cycle. I only have either one up and down or I have one down and up. I don't have a whole up and down and then back up again. I'm only getting half of the wavelength. I'm only getting one of these two halves. And so this whole length is half of a wavelength. And so that this equation should make sense in context. And so, but we can solve this for wavelength. We just need to multiply by 2 on both sides. And so we get that 2.4 is equal to the wavelength. And so the wavelength of the first harmonic is equal to 2.4 meters. And we can do this for the other ones. Let's go ahead and sketch them. The second harmonic, we would sketch it like this. We would go up and down. And so that's what one wavelength would, that's what one up and down would look like. But of course, as convention, we generally draw both up and down. So we draw like that as well. And look, that's one whole wavelength. That's one whole cycle. We go up and we're going down. And so, and that should make sense. This is our second harmonic. And so if we use the equation, then that means 1.2 is equal to 2 over 2 wavelength, because it's our second harmonic, so we plug in 2 there for n. And so we're just saying that 1.2 is equal to a wavelength. And so the first harmonic was equal to 2.4, and the second harmonic is equal to 1.2. And let's do the third one. Again, the sketch looks like this. And so that's what it would look like. That looks like 1.5. So about 3 halves of a wavelength. And of course, that's going to be what our equation is going to be equal to. But by convention, we're going to draw the bottoms as well. And so the length is equal to n over 2 wavelength. So 1.2 is equal to 3 halves wavelength. And yeah, that makes sense because, again, there's 3 halves of a wavelength there. And so we do this, we get, if we divide this by 3, we get 0.4. And so multiply by 2, we get 0.8. If you just want to put in your calculator, we just need to multiply by 2/3 on each side. Multiply by the reciprocal to get rid of it. And so we should get 0.8 meters. So these are all the wavelengths. And so it's not too math heavy, but it can be confusing, like, because it's a different equation than you're used to. You're not used to seeing n for like a certain nth harmonic. It's a different equation than you're used to seeing, but hopefully it makes sense. If it doesn't make sense, I'm actually getting a lot of these notes. I'm following kind of a structure from a website called Physics Classroom, and I'm going to actually be linking there to their next class, because I will not be here on either Thursday or Friday this week. So that's April 1st and April 5th. I won't be in class. I won't have any notes posted online. Okay, and so I'll actually be linking to Physics Classroom for basically a note session. And then the following class, I will post notes that go over the same stuff. And so, I won't just be leaving you guys in the dark for those notes. But if at all during this unit you're confused on certain topics, go to Physics Classroom. They don't cover simple harmonic motion very well, okay? And so make sure you're looking at my notes for that. But for everything waves related, so last class's notes, this class's notes, and then next class's notes, all of them, it covers everything. It covers everything we're going to talk about. And so it's a good place to go to. The units are waves and also sound. When it talks about sound, we're going to talk about that too. Next unit, we'll talk about optics, and I'll link there as well. With that, you should be able to complete the assignment. The assignment is, it actually is going to be filling in some notes/problems that are directly from Physics Classroom, as well as an assignment I made, which we'll be talking about doing some adding a waves and stuff like that. And then it talks about, I think there's a conceptual on some of the other stuff in this notes here. So the first part will be basically all standing waves, and then the last part we'll talk about some of the other conceptual we talked about today. With that, you should be good. Have a good day.